Okay, so the second thing we have to do is show that t respects scalar multiplication. You guys think you know how to write it down? Anybody get it? Let's see if I've got anything close to what you have. Basically, for scalar multiplication, I have a constant times my vector. So I'll call my constant k. In fact, let me put the formula here. T of k times v1 needs to be k times t of v1. So I have to be able to factor the constant out of the transformation. Okay? So to do that, what I'm going to need to do here is, well, use the formula again. This is just x times k p of x prime plus 2 times k p of x double prime. Does that look anything like what you guys have? No? Okay. It's all right. We're practicing. So this is just a constant times a vector. We're going to transform it. Here's the rule. This is really the key to everything, right? This is how you figure it out. Okay. When you're taking derivatives, what do you normally get to do with constants? Pull them out. Yeah, and in fact, can you see that that's really what you want to do? Let's take a look here. You're trying to get the k totally on the outside. So you want to be getting that k as far to the left as you can, right? So I can do that. I can take this k and pull it right out of the derivative. So it's k times x times p prime of x. And then over here I have 2 times k times p double prime of x. Right? And now what am I going to do next? Exactly. Take the k totally out of it, leaves me with x p prime of x plus 2 p double prime of x. Exactly. And the part in brackets is what? The transformation of what? P of x. Exactly. The transformation of p of x, and that's what I wanted to get, guys. So what I hope that you guys are seeing here is that you start on the left side, you do a bunch of equal signs, and get to the right side of these formulas up here. You start out with the whole thing together, and you're basically busting it apart. The transformation is supposed to respect addition and scalar multiplication. Just means you can bust everything apart. In fact, between these two properties, you can actually do something even more general. If you have an entire linear combination, this is just a very general thing. If you have an entire linear combination like that, if t is truly linear, you can pull all of the constants out and all of the plus signs out. So you can totally break this thing down. And this is a very, very common idea here. You can just totally bust it up. All the constants come out, all of the plus signs come out. Make sense? You guys with me? Okay, so that's really the upshot of what a linear transformation is like. Is that you can pull those things totally out of it. Okay, are we good on showing that t is linear? You need to practice that a lot. It's in the homework for tomorrow night, and I want you guys to get good at it. This is an example with polynomials, but you will also see other examples where you're dealing with matrices or traditional vectors or whatever. So, respecting addition and respecting scalar multiplication. You need to be able to check those two things. Okay? So far, so good. Okay. There's a part B now. We've already shown that it's linear. So part B is find a basis and dimension for the kernel of t. Let's see what's going on here. Find a basis and dimension for the kernel of t. I haven't talked about the kernel of t yet, so I need to kind of go over that. I'm going to just very briefly go over it with you, and I'll talk more about it tomorrow night, but it just helps to show you in advance. The kernel of t, by the way, is always going to be a subspace of V. So when you have t going from v to w, right, the v is the input set, and the w is the output set. We have inputs and we have outputs. On this example, the inputs and outputs are the same set. But in general, they are not. So in general, you have, I like to draw these pictures. Like here's v and here's w, and it's just a function. So you're just taking vectors here, and they get mapped over to here. So capital T just takes inputs and sends them across to the other side. Right? That's basically what a transformation does. Inputs on one side, outputs on the other side. Clear enough? The kernel of T. The kernel of T, this is a very important idea. The kernel of T turns out that that is the set of vectors in V. It's the inputs that get transformed to 0. Okay. It's the vectors that get transformed to 0. Okay? So let me draw my picture a little bit bigger so you can see it better. Okay. So let me draw a slightly bigger picture here. Here's V, here's W, right? So you have all these vectors just getting mapped across, whatever, right? But here, let's put our 0 vector in here. So each vector space, every vector space has a 0 vector, right? It's one of our axioms. Every vector space has a 0 vector. One of the properties that, and I mentioned this on the video, is that the transformation has to send 0 to 0. Any linear transformation must do that. In fact, that's a good way to show that something's not linear. If the 0 vector does not map to the 0 vector, then T is not linear. And you can stop. You don't have to do any more work. If you don't have a linear transformation, then you're not going to get asked any more questions, right? That's going to be it. The 0 vector has to go to the 0 vector, but there might be other vectors that also go to the 0 vector. There's nothing that says that you can't have multiple things going to the same place. Let me just move this arrow here. Okay, all of these vectors that I'm shading in right here, that shaded area, all of that is the kernel of T. The kernel of T is those inputs that get killed. Just think of it that way. It's those inputs that get sent to 0. Make sense? It's those inputs that get sent to 0. And that forms a subspace of V. So it's closed under addition, and it's closed under scalar multiplication. I'll show you, maybe I'll show you that tomorrow night. It's a subspace of V. Take my word for it. As soon as it's a subspace of V, though, I'm going to ask you a question. What's the basis? What's the dimension? So the question then might be, well, how do you find those two things? So you guys with me? Okay, so how to find a basis for the kernel of T. I'm just going to give you a quick little procedure and then let you guys see on this example how you do that. Basically, here's the process. Basically, here's what you do. You set T of V equal to 0. And solve for V. So you imagine that you have a vector that gets killed, and then you figure out, well, what vector is that? Okay, so which vectors are they that get killed? Does this make sense? I mean, that's the definition of the kernel. It's those vectors for which T of V equals 0. So how are you going to figure out what the kernel is? Well, you're going to set T of V equal to 0 and figure out which V's make that happen. Makes sense, right? If you just believe this is the definition of what the kernel is. It's those vectors that get killed. So let's try it on this example. Now here's the problem. If I do it on this example, problem 6, then what I'm doing is I'm going to set t of p of x equal to 0. And if I do that, well, then what am I really saying? I'm saying that x times p prime of x plus 2 times p double prime of x is equal to 0. And my goal is to solve for p of x, right? That's kind of how the process works. Difficulty of it, though, what makes it hard here, guys, is that most of us look at this and say, you know what, that means I'm solving a differential equation. This is a differential equation, right? It's an equation involving one or more derivatives of an unknown function. It's a differential equation. And what's more, it's a second order differential equation, which we didn't even study yet. Right, the only thing we studied in this book so far is chapter 1 about differential equations, and that was just first order differential equations. We never studied second order differential equations. So surely I'm not really asking you to solve this equation. Right? So this is very hard right now. So I am wondering whether anybody maybe has another idea about how to handle that. How are we going to be able, because I'm asking the question, and I'm putting it in the review packet, so we should be able to do this. Does anybody know what would be a way that we could figure this out? A way that we could figure out which polynomials actually are going to get killed. There's no matrix here, right? I have no matrix in this problem. If I was dealing, there are other examples where the kernel is really the null space, but that's for the t of x equals ax special case. This is not a nice problem, right? This is a very general type of example. All right, I'm gonna help you with this. Okay. I guess I can erase this for now. What you have to do, guys, is you have to go back and write your polynomial p of x as ax squared plus bx plus c. And you have to just brute force it in those terms. Okay? So here's what we're going to do. We're going to write p of x as ax squared plus bx plus c. And it's very easy to, of course, take, what are we going to need? We're going to need 2 derivatives of that. So let me just go ahead and figure out those derivatives. So p prime of x is going to be, what's the derivative of this? 2ax plus b. And what's the second derivative of this? There you go. Right. So that's what you have. Okay, now that seems like something we could work with, because here's the equation that we have, right? So let's just plug that in. So I have x times p prime, which is 2ax plus b, plus 2 times p double prime, which is 2a, and that is supposed to be equal to 0. Okay? If I take this equation and regroup the terms, what's the x squared coefficient going to be? 2a, okay, good. So let's write that down. 2a x squared. What is the x coefficient going to be? Just b times x, right? So bx. And what is my constant coefficient going to be? 4a, right? All I did there, guys, is I just regrouped the terms. I said, what's the x squared term, what's the x term, and what's the constant term? Right? Are we with me? Now, in order for this to add up to 0, if you have a polynomial that's going to add up to 0, isn't it true that every single coefficient needs to be 0? So look what's going to happen. This coefficient has to be 0. We're trying to figure out what p of x is. The goal is to solve for p of x, which really means solve for a, b, and c. Well, here's something that's going to help me do that, right? So the x squared coefficient is going to have to be 0. The x coefficient, which is b, has to be 0. And the constant term also has to be 0, right? You get actually a system of equations. This particular system is really, really easy. A and b are both 0. And notice what happened there, guys, is that c never got mentioned. It doesn't show up here. What's that tell you about c? It can be anything, right? It doesn't even matter. C can be anything. It's like the constant term. It kind of makes sense that C can be anything, because when you differentiate it either once or twice, it goes away. Right? So in this expression, when you transform your polynomial, who cares what the constant term is? It's going to get crushed anyway by the derivatives. So C is like free. C is like a free variable. So C is free. You could change it to a T if you wanted to, but I'll just leave it as a C. So guys, which polynomials are in the kernel? Can't have, A is 0, B is 0, but C is free. Every constant polynomial is in the kernel. So the kernel of T is just the set of C such that C is an element of R. That's it. It's just a constant polynomial. That's the only thing in the kernel. And remember, what is the kernel? The kernel is those inputs that get killed. Those inputs that get killed. Do you agree that a constant gets killed by this transformation? Plug a constant in for the polynomial. What happens when you plug it in? Oh, you differentiate it. It's gone, right? Oh, you differentiate it twice. It's really gone. It becomes 0. You have 0 plus 0. It's 0. It got killed. That's no surprise. It's no surprise that all the constant polynomials are going to be in the kernel. What maybe is surprising is nothing else is in the kernel. The only things that are in the kernel, I mean the A and the B, if you're going to be in the kernel, the A and the B both have to be 0. Which polynomials are in the kernel? Only the constant polynomials. Make sense? Now, what would be a basis for that? Because the question says find, I erased it. The problem is asking us to find a basis for the kernel. So what's a basis for this? You want to say it, don't you? One. One. Just one, right? Okay, guys. Bust out the variables. This is really silly. Right, you bust out the variables, that's what you get. The C busts out, and here, in all of its glory, is your one basis vector, right? Your basis is just 1 all by itself. It's just 1 all by itself. Okay, so that's your basis. All right, what is the dimension of the kernel? How many things are in the basis? 1. 1. There you go. The dimension is 1. Beautiful. Okay. Kind of silly, but the kernel is quite trivial in this case. Are you guys with me? Yes. You know what's weird about this problem that makes it a little tricky is that this is what you were given to work with, right? Showing that it is linear, which is what part A was, is easier to do by just leaving it as an abstract p of x. But figuring out what the kernel is better done by writing out explicitly what your p of x form is. Not all of these examples are this tricky, but for these polynomials, sometimes it works out that way. That it's better for proving the linearity to leave it like this, but it's better for finding the kernel to write p of x like this. Yeah. Okay. So that's the basis and the dimension of the kernel. Yeah. Go ahead, Everett.
If C always or also equals 0, then would there be no kernel? Or would
C equal to 0 would be the 0 vector then. And that would be one of my vectors that gets killed. Okay, so what are my vectors that we're talking? Every vector has this form, right? And every vector that's in the kernel has that form, because A and B have to be 0. So all of these guys are in the kernel, whether C is 0 or not, it's in the kernel. So 0 is in the kernel, 17 is in the kernel, pi over 19 is in the kernel, right? Any constant is in the kernel. Actually, so if I ask you which functions are in the kernel of the derivative operator, suppose your transformation is you're just going to differentiate stuff. I'm really just asking you which functions do you differentiate and they become 0? The answer is all the constants. That's what you learn in calculus. Which functions get killed by differentiation? Constants. Well, actually that's the answer we got for this problem too. We were doing something slightly more complicated than just a single plane derivative, but this particular transformation also kills exactly the constants and nothing else. Okay. Are we all right with the kernel idea? You guys are going to have a leg up on everybody else tomorrow, because I'm going to be talking a lot about kernel and range tomorrow night. So seeing it now is not a bad thing. You're going to get to reinforce it again, and then you can watch my video and reinforce it again. There'll be lots of chances to do that. Okay, there's a part C. You haven't had enough of this problem. Part C is find a basis and dimension for the range of T, which is written as RNG of T. We have the kernel and we have the range. Okay. So now I have to tell you another concept. Okay. So here's my picture that I keep coming back to. You know, I have all these vectors going over here. The 0 vectors are on the bottom. 0 vectors are down here. So here in this circle, that was the kernel of T. And the kernel of T is a subspace of V. Right? The range of T turns out to be a subspace of W. So let me draw a few more things on here. What is the range of T? The range of T is over on this side of the picture. The range of T, if I want to put it into very, very simple terms, is just the set of all outputs. You see, there could be elements in W. So in this example, W is like all quadratic polynomials. There could be elements in W that don't show up as outputs. And therefore the range would not include those. I give you an example, a really simple, before we do this example, I'll give you an even simpler example. Let's just go back to, I was just talking about the derivative operator. I'm just going to write it like this really quick, just the first derivative. So suppose you take a quadratic polynomial, P2, right? So imagine you're going from P2 to P2. You take a quadratic polynomial, you just take its derivative, right? Would you agree that there are polynomials in P2 that do not show up as outputs of taking a derivative? I mean, if you take ax squared plus bx plus c and you take its derivative, of course what you get is 2ax plus b. Well, 2ax plus b, that is not representing every quadratic polynomial anymore, right? The only things I'm actually getting as outputs, are these degree 1 polynomials. See that? So there's this, basically in your picture, there's this white space up here. There's these vectors that are not hit by transforming something. So for example, right here, you might have the polynomial x squared. Right? That's not in this shaded part for the range of t, because I can't get x squared out of this. what would it take? What would I have to differentiate in order to get x squared? Well, I'd have to differentiate 1/3 of x cubed. Right, you kind of go backwards. Well, 1/3 x cubed is not one of my inputs. So I'm not able to get x squared as an output if I don't have 1/3 x cubed as an available input. You guys see what I'm saying? Okay, so my point is, the range of t is just that part of w that arises as an output of the transformation by some vector from the input set. You guys know that there is a, this is just very general comment, there is a transformation, a perfectly valid linear transformation that takes every vector in the input space, and what the function does is it just kills it. Every single vector just gets killed. Actually, if that's the case, then the kernel of t is the entire v, right? Every vector is getting killed. That's what that's the definition of the kernel, is which vectors are getting killed. For this transformation where you kill everything, the kernel is everything. But what's the range? The range is which vectors are showing up as outputs. If I use this transformation, only 0 is the only output that we ever get. Every vector gets killed. So the only output is, so the range is just 0. The range is tiny. The kernel is huge, the range is tiny. For this example. This is like a trivial example. But it's a valid example nonetheless. So the range of t is just all the outputs that actually get hit. Kind of make sense? Yeah, go ahead, Everett.
Does the range include the 0 vector?
It has to, yeah. Because the 0 vector always gets hit as an output. Why do I know that 0 is always going to get hit? Well, because I have a 0 vector over here that always goes to it, right? So this guy for sure gets hit. The 0 vector will always be in the range of the transformation. But who knows? Maybe that's the only thing that gets hit. If this is my transformation, the 0 vector is then the only thing that gets hit. Right? Making sense? Maybe what will make you happier is if I just give you a procedure for finding the range of t. Because there's a nice procedure for it. That means you'd have to think less and just go with the flow of calculating it. Let me show you how to find the range of t. It's actually very simple. Oh, this is really, really nice. So I'm maybe going to go a few extra minutes here. I hope it's okay. If you have to leave, it's fine. But this will really help you. And maybe the sooner you see it and learn it, the better. Okay? Here's the deal. To find the range of t, here's what you do. You do 2 steps. There's sort of 2 parts to this. The first part is choose a basis, let's say v1, v2, up to vn for v. And then the second thing is, there's a very simple formula for the range of t. Turns out, what is the range of t? After you choose, by the way, you can choose any basis you want. It doesn't matter. You may as well choose the easiest one that you know. So like if it's p2 of r, I would suggest the basis should be 1x and x squared. Right? So you choose the easiest basis that you know. It doesn't matter which one. And then the range of t is simply the span. Oh, if it's the span of something, it's already going to be a subspace. So I don't even have to worry about that. And it's the span of what? Well, what you do is you simply transform all of your basis vectors. You just do this transformation. It's just the span of those guys. It's just the span of those guys. Does that make sense? Sorry?